Let's get started for the day. We were looking at the delta function, continuous time Dirac delta function, and then we were looking at its definition from the sequence of functions point of view, and that point of view gave rise to some paradoxes. So let us continue along the same lines and then see one more point that might seem surprising if you have not seen this before. So you are usually told that the delta function definition is this, that is, so this is 1, so the area under the function is 1, that is what we are used to, and then delta of t is 0 for t not equal to 0. So the question is, do the above two definitions define delta of t uniquely? So this is something worth asking. And for this, let us again go to the sequence of functions approach and then see whether we can infer something more. Actually, we have been using the sequence of functions approach to show that what problems can exist. In this case, we will use the sequence of functions approach for a plausibility argument. So for this, let us look at this. So this was one of the functions which in the limit appeared to converge to the delta function. So I think we call this as y delta of t, and then somehow we got ourselves convinced that this looks like the delta function in the limit. It becomes skinnier and skinnier, taller and taller, and area is always 1, and in the limit this seems to satisfy these two properties. Now let us look at this, the derivative of this. So let us look at y cap delta dash of t. So this of course has this form, which is easy to see. And the height of course is the slope, and the slope is 1 over delta square. Difference in y coordinates by difference in x coordinates. All right. And in the limit, as cap delta tends to 0, this seems to approach this function. So for each of these rectangular pulses, each part becomes skinnier and skinnier, taller and taller, and in the limit this is how this is depicted. This is the function delta dash of t in the limit, and this is what is called as the unit doublet, and this is the derivative of the delta function. Again, we are using sequence of functions to suggest a plausibility argument. Since we are comfortable with sequence of functions converging to delta, we are using the same approach here. Now clearly y dash delta of t, the area is what? It is 0. Okay. And so this seems to imply that this also is 0, right, based on the limiting ideas we have been used to in this context before. Okay. So at least this seems to suggest this. And what can you say about delta dash of t for t not equal to 0? Remember, if delta dash of t is this, in the limit as cap delta tends to 0, this becomes skinnier and skinnier, taller and taller. So what can you say about delta dash of t whenever t is not equal to 0? It is 0. Okay. So looks like the area under delta dash of t is 0, and delta dash of t is 0 for t not equal to 0. Seems reasonable based on what we have looked at so far. Now what about this? Delta dash of t plus delta of t for t not equal to 0, this function is 0. Very good. And then minus infinity to plus infinity, delta t plus delta dash of t dt, this area is 1. So clearly delta t plus delta dash of t also satisfies these two equations. All right. So now you see the problem with this. So this begs the question, what is the correct definition of delta of t? So the correct way of defining the delta function is as follows. So where f of t is continuous at t equal to 0. So this is how delta t should be defined. Any function that satisfies this is the delta function. Now, just to give you the larger picture, so mathematician Jan Mikusinski, he developed a theory of delta function based on sequence of functions in a very rigorous and careful manner. And Laurent Schwartz, French mathematician, developed a theory of delta of t based on what he called as the theory of distributions. And his approach is what is widely used today, and to understand that requires a lot more mathematical machinery. as far as we are concerned, we are happy with the sequence of functions approach to get some feel, but then all that I have done so far is to make you aware that there is much more to delta of t that goes on than what we are used to, and we do not have the mathematical training to appreciate it fully. We will use the general properties as listed here, and as you might have already encountered some of it before. Inside of integrals, delta function is fine, provided it is in product with a function that is continuous at the location of the impulse. And delta of 0 is really not defined. If you look at the theory developed, delta of 0 is not defined. Whereas in engineering textbooks, you will find that delta of 0 is infinity and so on. So, all these things are not careful development of the concept. The correct way of calling delta function is, in some books it is called as a functional, in some books it is called as a generalized function or a distribution. So, these are terms that should remind us this is not an ordinary function, and delta of t is not the only generalized function or a distribution. There are other members of this set, but delta function is the one that is most famous, most well known, and that is what we will be using for our purposes in this course. Inside of integrals it is fine when it is in product with the function that is continuous at the location of the impulse. So, typically we will do symbolic manipulations with delta, and if you are not sure as to what the underlying theory is, we might make mistakes in the symbolic manipulation. So, you have to be very aware of the limitations in our understanding of delta of t. As long as you are aware, that is fine. The reason why you are running into difficulty is, for example, suppose you consider function like y delta of t, and this is one for all cap delta for the y delta that I have shown, and what we are doing is we are applying the limit as cap delta is tending to 0, and then the flaw is in this step. Integral obviously is a limiting process. Here you have limit cap delta tending to 0. What we are doing is we are interchanging two limiting processes, and then we are taking the limit inside the integral sign, and then we think that limit cap delta tending to 0 of y cap delta of t is delta of t, and then we come up with something like this. So, the problem arises because we are interchanging two limiting processes and without being sure whether we are allowed to do that or not. So, under ordinary rules of calculus, there is no known function that satisfies the definition of the delta. Even this definition, that is, even this definition of delta, no known ordinary function can satisfy this. So, that is why you required people like Laurent Schwartz to come up and develop a whole new theory, and the theory of distributions as developed by him is considered to be one of the landmark achievements of the last century. So, there is a lot more going on here. If you want to learn more about the delta function at a more understandable level, you can look up the book by Kamler, first course in Fourier analysis by Kamler. So, this is one book you can look up, and then another book is Fourier and Laplace transform. This is by 4 Dutch authors. Both these books are by Cambridge University Press. So, you can get some feel for how mathematicians handle delta function. Unlike the loose and non-rigorous way that we handle delta in engineering textbooks. So it's not a function, even though we call it as a function, it is not a function. As long as you're aware of that and things that are happening with delta that is more than meets the eye, then you're fine. So this definition, that is delta of t times f of t dt equals f of 0. So that immediately gives us the fact that the area under the delta function is 1. So replace f of t by 1, and on the right hand side the answer is this function evaluated at the origin, which is 1, and sure enough f of t equal to 1 for all t is indeed continuous at t equal to 0. Therefore this is fine. So the so called area under delta of t is 1 actually follows from this. And what we are normally used to is that we are given these two definitions, and then this is taken as a consequence of the earlier definitions that we are used to, and we call this as the shifting property. Really this is the fundamental definition and the others are consequences. The other thing that we are used to when we deal with delta functions is that until you have delta functions in your armory, the derivative of a function at a point of discontinuity doesn't exist. But then we see that minus infinity to plus infinity delta of t dt is 1, and since this exists only in the infinitesimal interval between 0 minus and 0 plus, so this is really 0 minus to 0 plus of delta of t, this equals 1. And then what we do is we start to look at things like this: minus infinity to t delta of tau d tau. And the picture that we have in mind when we are doing this is we have this impulse sitting at the origin. So this is delta of tau, and minus infinity to t is nothing but the running integral of this. So we have two possibilities here. So if your t is less than 0, then the running integral value is 0. Therefore we say that this is 0 for t less than 0. The other possibilities of course is the value of t being greater than 0, in which case the running integral value is 1. And lo and behold, a function that is 0 for t less than 0 and 1 for t greater than 0 is nothing but our usual unit step function, right. Therefore we have this relationship minus infinity to t delta of tau d tau is nothing but u of t, and then we bring in what is well known to us. Then we say d by dt of u of t is delta of t, correct? Yeah, so this doesn't define what u of t is at t equal to 0, but so why is that a problem? Oh, you mean you are now asking whether this follows. So why is this? Yeah, so this really doesn't, that it not being defined at t equal to 0 is not an issue really. And to go from here to here, what are you invoking? Okay, I mean what first principles? Hey, what's the name? So this is fundamental theorem of calculus, correct? Okay, okay. If that was you were searching for, that's fine. All right. So again, we are doing symbolic manipulations here, right? We are treating this as an ordinary function. Fundamental theorem of calculus applies to ordinary functions. Delta of t is anything but we are happily using this, right? So anyway, so we leave it to the mathematicians to establish these things rigorously. And the picture that the engineer has of this is this. So this is u delta of t, and u delta cap delta dash of t. So this is between minus delta by 2 to plus delta by 2, and this of course is 1 over delta, and then we take limit as cap delta tends to 0. In the limit as cap delta tends to 0, this sloping part becomes more and more vertical. So in the limit, this becomes like this. So this indeed becomes u of t, and we are quite convinced that u dash of t is indeed the delta function. These are the kinds of pictures that we have as far as these operations are concerned, at least in engineering textbooks. All I want you to be aware of is you need a lot more rigor than establishing these things by these simple minded pictures. And just to make sure you have understood all these things properly, if you know the answer to this question, very good. If you don't know, it's worth thinking about till the answer to this becomes clear and there are no confusions about this. So this is x of t, and then this signal is applied to this circuit. So you can, R can be anything, it can be 1 ohm and 1 C can be 1 farad. So this is my x of t, and then the question is what is y of t, and the impulse response of course is 1 over RC e power minus t by RC u of t. So if the answer as to what y of t is very clear to you, then you have understood all these concepts very well. If not, based on whatever we have seen so far, go back and try to find what y of t is for this particular input and this particular circuit. Just to wrap up delta of t, so the way that we'd like to understand delta of t is a shorthand notation, because we are engineers, we deal with practical systems and signals. Delta of t is a shorthand notation for a pulse that is very brief. And in practice, all measuring equipment have finite resolving power. You cannot measure anything in practice with infinite precision. So, all practical equipment have finite resolving power. To within the limits of this resolving power, making this pulse any briefer, right, independent of its shape, as long as the area is maintained, you will not be able to observe any difference in the measured output. That is all. So, the shorthand notation for delta is for a pulse that is so brief, making it briefer will not make any difference in practice, because all practical measurements have finite resolving power. So, it is in that context we are using delta of t. Deriving or developing an underlying theory that is sound is completely different, and that is what the mathematicians have done. So, that what this means is, so given the finite resolving power of any measurement, making the pulse briefer while maintaining the same area, does not produce a measurable difference. Independent of the shape.